Hello and welcome to week 6 of Introduction to Healthcare and Business Analytics. And in this week's session, we're going to talk about data science, and it's a very interesting and growing field within analytics. And I want to give you a taste of what is in it and what is all involved with it. So we'll talk about data science. We'll talk about some of the key pillars of data science, the process of data science. What is big data and why is everyone's interested in it? And we'll talk about the process for how we use data science to answer questions and solve problems. So first of all, what is data science? Data science is quite simply the science of analyzing raw data and drawing conclusions about that information. And it involves things such as statistics, computer science, mathematics, data cleaning and formatting, and data visualization. Now, data science is a part of an overall data strategy. We've talked about this before in terms of the various types of analytics that are often used. So you see everything from descriptive and diagnostic and predictive analytics up into more advanced analytics, which will drive decision support and decision automation, such as prescriptive and cognitive analytics. And what you can see from this chart here is that as you get into more and more of these advanced analytic capabilities, you're able to use the data to drive more decisions and more actions by themselves. So there are several key components of a data science program within an organization, and we're going to talk about each one of them briefly here. The first is domain knowledge and what that all means. It's very, very critical. The second is the analysis skills that are used within that domain and within that data. The third is the computer science component itself and how that all works. And then finally, we'll talk about communications and its role within data science. So domain knowledge in data science is absolutely essential. You have to have a good fundamental understanding of the business areas that you are working with and the business areas that you are trying to model and you are trying to understand. That I have seen over many years within my own career, organizations which try to use IT to run analytics and run decision and run these types of things. And IT do not usually have the domain knowledge that is required to be able to be successful here. They may understand the technology, but that doesn't mean they understand the application of it in that respect. I just say somebody who may set up a spreadsheet on a computer may not know how to use that spreadsheet to model different parts of the business or different parts of the operation, nor should they be expected to be. So that domain knowledge is very, very important. And you have to know how to ask the right questions from the right people and to get the information you need to communicate that through the appropriate visualization tools. The next component is analysis skills, and this involves everything from linear algebra, multivariable calculus, optimization techniques, and this is where machine learning algorithms can play an important role in that. And this is an area that I would encourage all of you to spend some time looking at and thinking about. If you're getting into this in any heavy way, you're going to be getting exposure to statistics and probability. If you're doing anything involving predictive or prescriptive or cognitive analytics, you're going to be using statistics and probability to create risk modeling, risk scores, and it's going to be very important to understand how you use those different tools, how you can benefit from those different tools. And here is where you'll be doing things like everything from linear to multilinear to logistic regression to probability analysis. And this is a key component of understanding and mastering machine learning. Computer science includes a variety of areas within this field, which are all important to keep in mind. There are programming knowledges. There are languages such as Python, SAS, R, Java, and a variety of other languages. There are relational databases, which are a key component of data and data science. Databases such as Oracle, SQL Server, Teradata, Netezza, MySQL, Sybase. Any of these things will do that type of job. There are non-relational databases such as Cassandra, HBase, MongoDB, Redis, Dynamo. These are all non-relational databases. Now the difference between them, relational databases hold standard fields and columns that you might be expecting to see. If you were to sign on, say, to your student record at Salve, you were signing into a relational database. Whereas a non-relational database would be taking data in a more unstructured form for analysis, things such as Twitter feeds or YouTube comments or different type of stream text, which doesn't fit neatly into a specific table or field. Then there are distributed computing systems which can handle all this different track together. It's one of the most important skills to be able to handle a large amount of data because it can't be processed on a single system. So you may hear things such as data lakes, which is an implementation from Hadoop. And there are other systems out there which will handle this type of information coming in from multiple places and multiple areas. Now, I did want to talk a bit about machine learning specifically because it's an area that has generated a lot of discussion and a lot of interest within data science. And what is machine learning? It is essentially computer algorithms that can improve themselves through experience, through use of data. It is a subset of artificial intelligence and is closely related to computational statistics. So essentially what you do is you build a model based upon a set of sample data, also known as training data, because you're training the machines, and then you get the system to a point where it is making predictions or decisions, even though it's not explicitly programmed to do so. A subset of machine learning is also, as I mentioned, it's closely related to computational statistics, and mathematical observation delivers methods, theory, and application domains to this field of machine learning. And it is also related to data mining, which is where you explore data analysis through unsupervised learning. You are again getting into large pieces of data and getting insights, extracting insights from that data, different types of nuggets or pieces of information which might be useful to you. And there are, if you're getting into these type of machine learning algorithms, there are multiple libraries that are available in both Python and R and other languages for implementing these kinds of things. And machine learning is called machine learning because it uses data and neural networks that in many ways mimics the activities of the actual brain, which makes it a very fascinating field to study. Then the final pillar I did want to draw on was communications, and this is drawing conclusions from your analysis. And this is essentially, if you come up with an analysis or come up with an insight on your own and you don't share it with anybody, how useful is it really? So the communications is the report that you send to your boss or your team. It is the blog post, it's the presentation, it's the insights, it's the alerts, it's the different pieces which may come in to either alter an action or alter a workflow in a way that is going to get you to a more desirable result. So let's talk about a little bit about the roles and responsibilities for a data scientist. So that the data scientist has a number of different responsibilities in that area. They have a management responsibility in that they're supporting construction of futuristic and technical capabilities within data and analytics. They have an analytics function itself, which includes planning and implementing high-level statistical models and strategies, and developing econometric and statistical models for various problems and situations. From a strategy design perspective, they would be expected to work with the advancement of innovative strategies to solve problems and solve difficult business problems. And from a knowledge perspective, they'd be expected to provide leadership to support different technologies and tools, and also to create insights for the business at the most agile pace as feasible and possible. So let's talk a little bit about the data science process. So why do we need data science? There is an enormous amount of data that is available and being generated. And what's been happening recently is that up until recently, the amount of data that was generated was greater than the computing capacity to handle that data and to gain insights in that data. Well, in the last few years, that circumstance has changed, and now that with the advent of more and more inexpensive computing tools to be able to manage it, we are now capable of analyzing and processing much larger data sets than we ever were before. Up until recently, no one ever thought of processing data in petabytes, which is the next step above terabytes. And now we are capable of doing that because we have systems that can do that. So it simply gives us the means to solve problems that just did not exist before. These are the means to solve problems that didn't exist before. So let's talk. We talked a little bit about that process. Let's talk about what big data is. So it's everywhere. Every time you go on the web, or you do something, you're doing something which is contributing to that big data stream. If you go to your bank and you fill out a bank transaction, if you go to Amazon and you buy a piece of clothing, or you buy a curtain rod, that gets filtered into a stream of big data. If you go onto your bank and you make a withdrawal from your checking account, or if you purchase something, that goes into big data. If you make a post on social media, if you post about your cats on Facebook, that's going to find its way into a big data stream of some type. And this is real live, and it can be real live data in everything from engineering plants to casinos. So you could be in an engineering plant and you're using real-time data to monitor the productivity and efficiency of certain equipment that you have. If things fall below a certain threshold, you'll get an alert on that. That's using big data. Casinos could be something as mundane as looking at traffic outside of a certain group of slot machines. Are there people walking by there at a pace that we expect? Should we be moving things around to accommodate different traffic and different people? I was at a presentation a couple of years ago at a SAS conference, and they were talking about some analysis tools that were written in SAS that were analyzing big data. And what they were doing is they were looking at a specific company, and they were analyzing all Twitter feeds and highlighting out any kind of comments about that company, and you could see metrics that were going up and down in a real-time basis as they were analyzing customer interactions, customer comments, or customer queries about different parts of this business, and you could see how those type of perceptions were happening in real time. So now that we talked about how big data is everywhere, I do want to back up just slightly and just make sure that we're all on the same page in terms of what actually is data. Now, I know we're in week 6 in this course, but I do want to make sure everyone has a common understanding of that. What is data? It is a set of values of either qualitative or quantitative variables, and this requires that we have a set of values to include in statistics. It's called a population. So qualitative variables are not something that you are going to necessarily sum up or divide or average. They are usually things like, what country are you from? What zip code do you live in? What is your marital status? What is your gender, your race? These are things that you're going to be counting, but you aren't going to be summing in any way. They're not numbers that are going to be held in a way that you're going to be using numeric calculations with them. You may use a number as a code, but it's not a number that you're going to average. Now, a possible exception to this, and I say possible, is Likert scale. These are numeric values that have an order of 1 to 5. So, say for example, you're given a survey, and you're given a statement, and you're asked to respond to a statement to whether you strongly disagree, somewhat disagree, neutral, strongly, somewhat agree, or strongly agree. That's going to give you a score of 1 to 5. That's called a Likert scale. That's a very common survey tool. Now, there are some situations where people may take a Likert scale and they will average it, and you see this in things like top box scores and other customer satisfaction scores, especially within the healthcare industry. You will average these components together. This is something, by the way, which gives many statisticians and people like myself the heebie-jeebies, and that's a technical term, because if I were to give somebody a rating of a 3, and you were to also give somebody a rating of a 3, your idea of a 3 and my idea of a 3 may be very, very different. You may be with a certain company. If you're asked to grade their performance and you think it's only so-so, and you're a very, very tough grader, and I'm not, and I think, well, it's fine, it's no big deal. Our numbers aren't the same, but they're being recorded the same. So when you average them, you can get yourself into some questionable situations there. I had a statistics professor when I was in graduate school who was very adamantly against doing that, but you do see that on occasion. So I put that in there as a kind of an exception as far as qualitative data is concerned. Now let's talk about quantitative data. Quantitative data are variables which measure quantities in some way, and they are numeric and they're on a constantly ordered scale. They may be real values, at which point there are decimal points up to whatever type of degree, or they could be integer values. In many cases, they are qualitative values. They are qualitative values. So weight, height, age, blood pressure are all qualitative values. Sales, like a money transaction, is a quantitative value. You know, any of those things which have numeric values that you can measure and you can average and you can divide and multiply, those are all qualitative values. So let's talk a little bit about data science in action, how that all works. So there is a basic process. And I use the analogy needle in a haystack. That's often what you're doing with any kind of data science or data analytics process. So you're going to form a question, you're going to find and you're going to generate the data that deals with that question, and you're going to explore and model the data for that question. So every project starts with a question that has to be answered. It is essentially a hypothesis. Think back to the use cases that we spoke about in earlier weeks. What is the basic research question that you're trying to answer? What is it that what is going to define success for you? You can't have an encounter issue with this. You have to know what you are going for. So forming a question is the first important step in the process. You need to have your questions clearly defined and be prepared for further questions to arise as you perform the analysis. And you may start with something and it's going to generate more questions and more questions. Oh, I didn't think of that, or I'm going into this level of detail and this level of detail as you go to analyze a question or analyze a process. I was involved in a project recently myself where we were looking at readmissions, and one question begat another, and it helps us get to a point of as we ask more questions, we get to a point where the answers we're developing have more meaning and they have more power. So the next step is you're going to find and generate the data. So how are you going to answer the question? What information are you going to get? Is it going to be in a random format? Is it going to be in a structured format? How can you gather more data, and how can you then determine what data is real and what data is irrelevant as you go ahead and find it? And this is a fundamental issue in terms of working with data. So this involves getting at your data quality, many of the things that we talked about earlier in the course. Remember the dirty windshield. Poor data quality is like a dirty windshield. So if you're not able to get a handle on your data quality, you're not going to be able to be seeing where you're going as well. So that's a key component to finding and generating the data that you're working with. And the next piece is exploring and modeling the data. Once you've got some of those other questions you've answered, now you're going to start exploring the data. You want to pre-process the data for modeling. You want to find differences and connections amongst the various factors of the data, and then you can start to run some exploratory analytics. Start to ask yourself some questions. Start to dig into some different things. What if this? What if this? What if this? Then you want to model the data. If you're getting into machine learning, then you're getting into training and testing. You're going to create that initial training set. You want to get at the different learning methods, such as classification and clustering, or get into some statistical or machine learning techniques to analyze the data and answer your questions. And then at that point, then you can start to think about how can you communicate that data? What is the means that you're going to use to communicate that data? And then how can you get to a point where you can communicate something, or you can express something in a way which is going to make a difference within your organization. So that's a summary of data science and the kinds of things that it means. It is an area that could frankly be an entire course here at Salve, and it is actually my hope that it will be. I would love it if we could have somebody come in and be able to teach that on a more detailed level, on a more advanced level. The purpose of this course is to give you a foundation and to give you an introduction of these various components, so that you can decide which pieces you may find more interesting. This, for me, is kind of the interesting stuff, getting into some of the more advanced areas that you can use data, and you could be able to use data to solve problems and work within organizations. So that's going to wrap up that piece for this particular week. And as far as our online discussion goes, this is going to go back a little bit in terms of some of our data visualization and representation processes. But I want to discuss how policymakers, and that includes yourself, should be on the lookout for misleading arguments and positions and other logical fallacies. And one of the things that's very important as you're getting into data science and machine learning and cognitive analytics is that it is very, very easy to get tripped up on your own biases. So how would you react to your own organization if they were to employ tactics either deliberately or inadvertently, which would lead you to be tripped up by some of these logical fallacies? So I'd like you to think about that. And I'll also be putting up another TED Talk dealing with machine learning this week that you can go through and see what somebody else is saying about it. So that's going to wrap up the discussion for this week. I have been reading through your papers in terms of your drafts and your outlines. I like the direction most of you are going in. And if you have any other questions, please feel free to reach out, and I will look forward to seeing you on the discussion sections, and please feel free to reach out. Thanks very much.